In the last lecture, we have learned that if two elements of PSL2 are or PSU11, they commute with each other, so then they have the same fixed points. So in this lecture, we'll learn about some algebraic properties of Gaussian groups. So we'll prove that, so if in a Gaussian group, if all the elements have a common fixed point, then that group has to be a cyclic group. So using that, we'll prove that a Gaussian group, it does not contain Z cross Z. Or in other words, Z cross Z, it is not a Gaussian group. Okay, so let me begin. Okay, the first theorem is the following. So let us take a Gaussian group and suppose all the non-identity elements of that Gaussian group have same fixed point set. So then we'll prove that that Gaussian group, it is a cyclic group. So let us begin with a Gaussian group gamma, and we have assumed that, so if I take two elements T and S such that they are not identity and fixed point of set of T is same as the fixed point set of S. So then by our previous lemma done in previous class or previous theorem, so this T of S is equal to your S compose T. So T and S, it commutes with each other. So T belongs to your gamma. So suppose this T is hyperbolic. So then, so this will imply that all the elements of this gamma are hyperbolic. Because, so we have assumed that, so if I take any other element, let us take S or S prime. So fixed point set of S is same as the fixed point set of T. And T is hyperbolic, means fixed point set of T is 2-point sets. So then fixed point set of that S prime will be again a 2-point set. So that will imply that this S prime is hyperbolic. Yeah. So because of that thing, so all the elements of this gamma are again hyperbolic. Now let us assume, so with the laws of generality, we can assume that Tz, again it is of the form lambda z. Right. And so this T, it belongs to your gamma. So now therefore for all S belongs to your gamma, fixed point set of S is equal to your 0 infinity. So because fixed point set of S is same as the fixed point set of T, fixed point set of T is equal to 0 infinity. So therefore fixed point set of S is 0 infinity. And Sz will be of this form mu z for some mu real number, mu positive number, and mu is not equal to your 1. Okay. So now, so what we want to prove is the following, that this gamma to be a cyclic group. So we need to find a generator for this cyclic group. So how to get that generator? So we have assumed that one element, let us take that element to be T, so that is hyperbolic. So let us take lambda naught to be the infimum of all those mu such that this isometry Sz equals to mu z, it belongs to your gamma, and mu is greater than 1. So lambda naught is defined. So next claim is this lambda naught is greater than 1. So let us take Az equals to lambda naught z. Okay. So yeah. So this gamma, so this will be, so what will prove that this gamma is generated by H. So Hz is equal to lambda naught z. Okay. So now there are two claims. So one is, so this lambda naught is greater than 1. And if I take this Hz equals to lambda naught z, so this group gamma is generated by this H. So why this first claim is true? So this lambda naught is greater than 1. So first of all, note that this lambda naught, because it is the infimum of all those mu, mu is greater than 1. So this lambda naught, it has to be greater than equals to 1. Okay. So now suppose, so I have to rule out this case that lambda naught is equal to 1. So I have to rule out this case. So suppose there exists mu n which converges to your lambda naught and Sz equals to mu nz. So this map, it belongs to your gamma, and this mu n, so these are my greater than 1. So lambda naught, we have assumed it to be equal to your 1. So this, okay, so Snz is equal to your, so Snz is equal to your mu nz. So this Snz, so mu n, it is converging to 1. So Snz will converge to your z. So this implies that this Sn, so this will converge to your identity map. And this Sn, it belongs to your gamma. And gamma is a Fouchian group. So it is a discrete group. So this will give you a contradiction. So this will prove that, so this contradiction will prove that, so this lambda naught, so this is greater than 1. So this lambda naught, it is greater than 1. Now the next claim is, so this gamma is generated by H, where this H is equal to your, Az is equal to your lambda naught z. So now let us take some element fz equals to mu z belongs to your gamma, where this mu is greater than 1. So claim is the following. So mu is equal to lambda naught to the power n for some natural number n. So if this is not true, so if mu is not equal to lambda naught to the power n for all natural number n, so then, so what will happen? Okay, so we'll get some n naught. So we'll get some n naught such that, so this mu, it will lie in this open interval lambda naught to the power n naught and lambda naught to the power n naught plus 1. So mu will lie in this open interval. So this will imply that 1 is less than mu by lambda naught to the power n naught less than lambda naught. Yeah, so we have this thing here. So we have this thing here. We have this inequality here. And this mu by lambda naught to the power n naught is less than lambda naught. So this is basically this map. So here it will be your lambda naught to the power n naught. Yeah. So this map, so it belongs to your this gamma. So we have assumed that this fz equals to mu z, it belongs to your gamma. Yeah, so this map fz equals to mu z, it belongs to your gamma. And also note that this map h z equals to lambda naught z, it also belongs to your gamma. So why this is true? Okay, so h belongs to your gamma. So this needs a proof. So let me write it here. So this lambda naught, it is the infimum of all those mu such that, so this mu, it is greater than 1, and z goes to this map mu z. So it belongs to your gamma. Yeah. So that is the thing written here. Okay. So we can get hold of a sequence mu n converging to this lambda naught, and so this mu n, it belongs to this set. So mu n are greater than 1, and so this maps, all these maps belongs to your gamma. So from here, so if I take Sn z to be equal to your mu n z, so this Sn, it is converging to this map, z goes to your lambda naught z. So yeah, Sn is converging to this map, and now, so this gamma is discrete. So this will tell you that, so this Sn, so this will be an eventually constant sequence. So this, yeah, so the sequence Sn will be eventually constant. So this will imply that, so this mu n sequence will be eventually constant, and for all large mu n, this will be equal to your lambda naught for all large n. So yeah, and this mu n we have taken from the set here. So therefore, so this uh, z goes to lambda naught z, that is this h map. So that will be again belongs to your gamma. So this will prove that h belongs to your gamma. So okay. So therefore we have shown this thing. So h belongs to your gamma. So this requires a proof. So that thing we have proved. So any power of h, so that will belong to your gamma. So any negative power of h, so that will also belong to your gamma. Yeah. So now this map, it is the composition of, so this is equal to your S compose h to the power minus n naught z. Yeah. So because of this thing, so this map will belong to your gamma. So which is a contradiction. So which is a contradiction? Why? Because so this, yeah, so this map, it belongs to your gamma, and mu by lambda naught to the power n naught is less than lambda naught. And this map, it belongs to your gamma. So therefore, we have something less than the infimum. So something less than the infimum such that z goes to mu by lambda naught to the power n naught z, it belongs to your gamma. So this is a contradiction. So the contradiction is arising because of this assumption. Because of this assumption. So contradiction is arising because of this assumption. So therefore, mu will be equal to lambda naught to the power n for some natural number n. Yeah. So therefore, so this f, so this will be equal to h to the power n for some natural number n. So therefore, what we have proved that, so this gamma, it is a cyclic group generated by this h. So if gamma contains a parabolic element or elliptic element, so the proof is exactly the similar in the similar way. So I'll not do that thing. So I'll leave that as an exercise. Okay. So now, as a corollary of this thing, so one can prove that so every abelian Fouchier group is cyclic. So if I take an abelian Fouchier group, so two elements will commute with each other. So then they will have the same fixed point. So in fact, in that abelian Fouchier group, so all the elements will have same fixed point set. And by this theorem, so that group will be a cyclic group. Okay, so every abelian Fouchier group is cyclic. So Z cross Z, it is an abelian group and it is a non-cyclic group. So it can never be a Fouchier group. Okay, so the next theorem is the following. So let us take a non-abelian Fouchier group. Then we'll prove that the normalizer of that group in PSL to R is Fouchier. So what do you mean by normalizer? So G is here PSL to R. So all those elements G such that G gamma G inverse is equal to gamma. So gamma, it is a normal subgroup is in this normalizer. So first let us take a sequence Tn in this normalizer and let us assume Tn converges to T. So we'll prove that first this T, it belongs to this normalizer. So this is the first claim. This is the first claim. So let us take any S belongs to your gamma. And Tn, it belongs to the normalizer. It means that Tn inverse, it will again, it belongs to gamma. Because Tn, it belongs to the normalizer of gamma. So Tn converges to T. So that will imply that Tn Stn inverse, it will converge to your Tst inverse. So this is very easy to verify. And Tn Stn inverse, it belongs to your gamma. So we have started gamma with a Fouchier group. So gamma is a Fouchier group. So this means that, so this sequence Tn Stn inverse, so this will be an eventually constant sequence. So therefore, we have this thing. So Tn Stn inverse is equal to your Tst inverse for all large n. And note that, so Tn Stn inverse, it belongs to your gamma. So therefore, Tst inverse, it will belongs to your gamma. So we have taken S belongs to your gamma. So S is an arbitrary element. So we have proved that Tst inverse, it belongs to gamma. So therefore, T belongs to the normalizer of this gamma. Okay. So next thing, so again, yeah. So we have proved this thing that you have, if you take a sequence Tn, in the normalizer such that Tn converges to T. So we have proved that T belongs to the normalizer. So to prove that this normalizer is a Fuchsian group, we have to prove that this sequence Tn, it is an eventually constant sequence. So Tn is equal to T for all large n. Suppose not. So the sequence Tn, it is a, we can take it to be a distinct sequence. So suppose not, so then, okay. So Tn converges to T, so T inverse Tn, it converges to your identity. So T and Tn, it both belongs to the normalizer. So therefore, this Pn equals to T inverse Tn, it belongs to the normalizer. And Pn converges to identity, we have assumed. And also because we have assumed that Tn converges to T, it is not an eventually constant sequence. So therefore, this Pn is not equal to identity. We can take Pn not equal to identity for all n. Okay, so now let us take any element S belongs to gamma. So Pn, it belongs to the normalizer. So Pn S Pn inverse, it again it belongs to yeah. Uh, Yeah, so you have taken S belongs to gamma. So Pn, it belongs to the normalizer. So Pn SP inverse, again it will be, it will belong to your gamma. I also note that Pn is converging to identity. So therefore Pn SP inverse, it will converge to your S. Again, gamma, it is a Fuchsian group. So therefore this sequence, it will be an eventually constant sequence. So therefore Pn SP inverse, Pn inverse, so this will be equal to S for all large n. So this will prove what? So the fixed point of S is equal to your fixed point of your Pn. For all n greater than equals to, let us take it to be ns. Now let us take S prime belongs to your gamma. So again, you will get an S prime such that for all n greater than equals to ns prime, fixed point of S prime will be equal to your fixed point of Pn. Okay, now let us take n to be greater than equals to ns and ns prime. So for that Pn, fixed point of S will be equal to fixed point of Pn, and fixed point of Pn will be equal to fixed point of S prime. So therefore, fixed point of S prime is equal to fixed points of S. Again, by the theorem we have done in the last class. So this S and S prime will commute with each other. And this is true for all S and S prime belongs to gamma. So we have taken S to be an arbitrary element and S prime again to be an arbitrary element. And we have proved that they commute with each other. So this proves that this gamma is abelian. But we have started with gamma to be a non-abelian group. So there is a contradiction. So this contradiction is due to this assumption that Tn, it is not an eventually constant sequence, so it will be an eventually constant sequence. So this Tn is equal to T for all large n. So that will imply, so this normalizer is a Fuchsian group.